So with that, now let's get into the stuff. The first thing is we will talk about what we call an architecture. It's called ISA, or Instruction Set Architecture. What an ISA means is it's essentially an ISA. This is essentially the API, if you wish, API, which includes the function calls or the like structures, for the CPU. And this is what like in this case, in a formal way, ISA. And remember that different ISAs, for example, x86 IA32, it's an ISA. x86 64, that's an ISA. ARM, that's an ISA. And like with this, for example, you like the fact that, for example, x86 64, you can if the ISA is the same, okay, you can buy an Intel processor or maybe an AMD processor, but they still they will count it as the same ISA. There will be, of course, minor changes, but at their core they overlap quite a lot. And within this, basically, what we define an architecture is that the parts of a processor design that one needs to understand to write assembly and machine code. And specifically, it requires what's the instruction set specification and what are the registers. So we will make this concrete in a second. Architecture is the design, but which instructions are supported, what are their binary representations, how many registers do we have, what are their sizes, what are the etc. etc. Okay, and then there's the microarchitecture. Microarchitecture is the implementation of the architecture. And remember that, for example, when I said x86 ISA, like x86 ISA, so you can have the same, it's just like that you have this library. It is a certain, API. Now you can implement the same functions by a different library. Okay, the implementation will be completely different, but the function definitions may be the same or will remain the same, and that's a different implementation. That's what we mean by a microarchitecture. Okay, for example, with x86 ISA, you will have two different microarchitectures, where, like I say, Intel and AMD. Okay, so these basically are different microarchitectures. This includes a lot like a cache size, core frequencies, and so on. And then we have this the different codes. We have the machine code, which is the byte level programs that the processor executes. This is what we call the binary executable. That's not readable. And then we have the assembly code. This is the text. It's just a low-level text code for this. So here we have your Intel's, different ISAs and ARM. So let's look at basically what an ISA means. And this is the assembly machine code view. Okay, so here's our CPU. And by the way, we will design two different CPUs from scratch. Okay, so there's just to get you excited. And on the CPU, we'll have registers, which you know what they mean. Okay, and we have the condition codes and the PC. And then we have a memory in which we have then we send addresses, data, and instructions, and your code, data stack, and so on. Okay. So from a programmer's point of view, we have a PC as a program counter. It's a special counter. It's just another register. It contains the address of the next instruction, or called RIP in x86-64. We have a register file, which is the set of registers in a pool. Okay. We have condition codes, which store information about the most recent arithmetic or logical operation, which is used for branching. We can see this. We'll look at the memory, which is byte addressable array, code, user data, and stack. So first, let's go over stuff here that's turning C into object code. So first, we will compile is again whatever I write here, and this is also you can use the book. Okay, you should try at home. Okay, on your machine right now. So with this, you can have you can compile your code, okay, into an executable. And so there are a lot of flags. Okay, for example, what this says is going to use basic optimizations. And as a result, you will have this binary file in here. Now, this whole thing actually takes multiple steps, which we have covered during the first lecture. For example, when you compile with -s here, then you will get an assembly program, which is a text, and it's with the s.s extension. And then when you can compile it as with the store as, and then you get an object program, which is a binary. And then in order to get your executable, you will be running with the linker, which links these binary code with some static libraries, and to get your final execute. So let's do this. You can just write this code. Here's our sum.code here. Okay, and when we look at here, so here's our, let's see, I do a sum store. Let's see, it's long x, long y, and then long destination. And then I define, like, here's another function definition called plus, which takes this. Its implementation is not available here. And this is basically, it calls it with plus, and then it puts the result into the location pointed by the destination. Now, if you compile this on a call machine, okay, with this command, the -s command, then it produces this file, sum.s, which is here. Okay, it has more stuff, but if you look carefully, then you'll get a code that's like this. Okay, so here you'll see that let's say that here's the function sum store, and then we have push q rbx, move q rdx. So these are register names, which you'll learn in a second. And then after that, you call plus another function, and then you move rax to rbx with parentheses pop, and then return. Note that when you compile, you may get different results on different machines, Linux, Mac OS, due to different versions and different compiler settings. But you will get some sort of this. But this is the assembly code, which is in text. Now in assembly, note that it's only certain data types are supported. You support integer data, okay, 1 to 4 8 bytes, which, and then the data values, addresses. It supports floating point data of 4, 8 to 10 bytes, and a code, which is the byte sequences encoding a series of instructions that we are shown here. But there are no aggregate types such as arrays or structures. Okay, there's no such thing. Okay. And just continuously allocate bytes in memory. And in this basically series of lectures, you'll understand basically how we can implement structures, arrays of structures, or functions, and so on. So for the assembly language, remember, we had instructions, things like move q, okay, or add q. Okay, these are all different instructions. They are very primitive. And these operations, they perform an arithmetic function on register or memory data. So typically we have basically some of them transfer data between memory and registers, loading the data from memory into register, or store register data into memory, or some of them transfer controls like unconditional jumps for form procedures or conditional branches. You'll again see them in detail. So when you look at the executable, for example, if you take the sum store here, you will see that this executable is actually represented in 14 bytes. Okay, and if you remember, in our assembly code, we had things like move, rax into rbx. Now this is a text. Now this is encoded in a binary, using these bytes, and the length of the instructions, it can be 1, 3, or 5 bytes, and this code starts at address 595. And this is what you will see in the .o file, where we have this binary encoding of each instruction. It's a nearly complete image of the executable file. The only thing that's missing is, for example, take your Hello World program. In your Hello World program, you just make a call to printf, okay? And this printf code was written by someone else, compiled in a different way. So it's only saying that call printf, but it doesn't have the link to that. So those links between code in different files, okay, they're basically resolved by a program called linker. Okay, linker resolves references between files. Okay, and for example, we have these static runtime libraries for used functions like malloc or printf. So these are basically programs that are written in a different way, in a different file. They were compiled, and they have basic code, and then basically it combines them with our code. Okay, and sometimes we have some libraries that are dynamically linked, where the linking occurs when the program begins the execution, as opposed to compile time. In a dynamically linked thing, linking is we'll say that we have statically link. In this case, the linker works at compile time, whereas in a dynamically linked link, then linking happens at. So let's have an example on how it works. So here we have, for example, in the C code, maybe we have an instruction T is assigned to the point located by destination. Now, when we look at the assembly code, then this is translated into an instruction, say move RAX percentage into pointed by RBX. This is moving 8-byte value into a memory, and where we have T, it's stored in the register RAX, destination, the address is stored in register RBX, and stardest is actually represents memory of RBX, which is represented as in parentheses of RBX. Okay, we will see this for this. And then when we compile this into object code, then this has this 3-byte instruction, which is 48, 89, and 03, okay, which is stored at this address. So this is the object code for the corresponding C code. Now, given an object code, you can actually disassemble. Okay, disassemble means get the object code from object code into assembly. Not that this is binary. Now this is text. Okay, so for example, if you do object dump minus the sum, which was one executable, this is also object file, then you get this. Okay, so it translates that the 53 actually encodes push RBX. Okay. 4889 D3 that encodes move RDX RBX. This encodes call queue, etc., etc. Okay, and you will be using this. Whatever I show here, in about 3 weeks time, you'll be masters of this. Okay, and this when we have this, then it can be run as a completely executable or as a .object file. Now, apart from object dump, what you will actually be using is GDB. This GDB, it's a debugger, it's a GNU debugger. And so you'll be, note that there are like a lot of, you need to understand basically its commands. And what you need to do is, again, in your first assignment, you'll be learning all the commands and how it works. And for example, you can do, once you load this with sum, okay, this is the object file here, then it gives you a prompt, and you say disassembled some store, then you'll be reading this, you'll see this. Then with this, then you can, for example, it has descriptive commands to examine the 14 bytes starting at some store, and then you'll get this done. This will be, you'll be learning this short. Now, what can be disassembled? Well, you can disassemble anything, okay? In the previous versions of this basically slides, we had the Microsoft's words, okay, executable here, but then they changed their end user license agreement, which stands for EULA. Okay, remember when you run your program first time, there's this thing that do you accept? Okay, and so when you do that, it says that reverse engineering is forbidden by Microsoft. Okay, that's why in the newer slides we don't have this, but we can get this. If you have this executable, you can disassemble it. And anything that can be interpreted as executable code, then it's done. And once you do it, then you have the possibility to understand what it does.